Hello everyone, welcome back to Deeksha Karnataka YouTube channel, and in the Masterstroke series today I am going to discuss dual nature of radiation and matter, a medium important chapter. 3 to maximum 4 question comes from this chapter. So obviously if you are preparing for KCET you cannot leave out this chapter because questions are relatively easier. We will see what type of questions, what are all the formulas from where the questions might come. So let's see the important concepts. Electron emission, different types of electron emission. Then obviously the chapter is dual nature of radiation of matter, but sometimes we call this chapter as photoelectric effect. So photoelectric effect is another important part. Then observation implication from the observation of photoelectric effect experiment. Okay, then we have Einstein's equation, the most important concept, most important part of this chapter. Then we have photons and obviously de Broglie wavelength. This is also super important. Okay, now what are the electron emission? We know that there are 3 types of electron emission. First is thermoionic emission, emission of electron from metals by heating. If you heat some metal, the metal will emit some electrons, that is called electron emission, thermoionic emission. Next is field emission. If you apply very high electric field, again metals emit electrons, that is called field emission, and the range of the field is 10 to the power of 8 volt per meter or Newton per coulomb. So 10 to the power of 8 Newton per coulomb electric field if you apply, then there is a chance of getting electrons, that is called field emission. But today we are not going to discuss about these 2 emissions. We are going to discuss about photoelectric emission. Okay, so what is this? So if you light up a metallic surface, okay, with certain frequency of light, then that metal surface tend to emit electrons, that is called photoelectric emission. Okay, and that is very important for a lot of applications. Okay, now let's move on. Photoelectric effect. So okay, so photoelectric effect is basically when you are lighting a metal surface and you are receiving the electron, the effect itself is called photoelectric effect and the emission is called photoelectric emission. Now Heinrich Hertz is the first person who observed this phenomenon a lot of time back, and even before the discovery of electron itself, he observed that when you are lighting some metal, okay, basically we will see that, and that surface is basically emitting negatively charged particle. Okay, later on it was came to know that negatively charged particle is nothing but electron. It was done even before the discovery of electron. That is why it is very interesting. When light falls on a metal surface, some electrons near the surface absorb the enough energy from the incident radiation to overcome the attraction of the positive ions in the material of the surface. After gaining sufficient energy from the incident light, the electrons escape from the surface of the metal into the surrounding space. So basically we know that a metal always have some freely moving electrons. They are loosely bound to the metal, but they are not completely free. Free means if you can take those electrons out, definitely you will say that electrons are free. But in this case electrons are not free. They can move through the metal, but still they are bound to the metal. Now if you light it up with suitable light, then those electrons becoming free. That means they are out of the metal surface. They are no longer bound to the nucleus of their respective element. Okay, and as I said, electrons, even though I have mentioned here electrons were yet to be discovered when Hertz observed this. Okay, he said that some negatively charged particle is coming out. Okay, now obviously if you want to do some career guidance, if you want to become an engineer in future or to become some expert in pharma sciences, then definitely you want to go through our product, which is Abhyas KCET test series, which will start from 17th of March onwards. 4 free tests are already available. If you have not yet registered, you can register yourself through the link given in the description and check for your yourself what all you are going to get, and once you are satisfied you can purchase this. 1498 is the price, excluding PU2 test series. PU2 test series was given for 1 rupee during the test exam. Now PU2 test series is no longer available. You can purchase it for 1498, and what you will get 31 paid tests along with their detailed video solution explanation by us, and you will get chapter wise one shot revision videos. You will get chapter wise insights for last 5-year KCET paper. So how the KCET paper was, what are all the different types of questions came, and what type of questions you can expect in your upcoming KCET 2025 exam. So for that you have to practice, and practice means you have to take Abhyas KCET test series immediately. Okay, now let us go through the next part of our lecture, that is photoelectric effect. It was found that certain metals like zinc, cadmium, magnesium, etc. responded only to ultraviolet light, okay, for observing photoelectric effect. However, some alkali metals such as lithium, sodium, potassium, cesium and rubidium were sensitive to even visible light. Okay, all these photosensitive substances emit electrons when they are illuminated by light. After the discovery of electrons, these electrons were termed as photoelectrons. The phenomena is called photoelectric effect. Obviously, photoelectric means, photo means light, electric means obviously current, associated with current, so that's why it is called photoelectric effect. Now this is Hallwach and Leonard's observation. Okay, now let's move on. Effect of, now we will discuss different effects on photoelectric effect. First is intensity of light on photocurrent. Intensity means how bright the light is or how dim the light is. Okay, so if it is a very bright light, we will say high intensity. It is a very small dim light, then we will say it's a dimmed light. Okay, now the number of photoelectrons emitted per second is directly proportional to the intensity of the incident radiation. So if you see that intensity of light and photoelectric current, it's a direct proportional relation. Direct proportional relation means it's a straight line and it passed through the origin. Okay, now these type of graphs you have to remember, because in KCET exam they will give you, they might give you graphs and you will be confused which type of graph for what. So for intensity of light and photoelectric current, they are directly proportional. If frequency is not involved, then obviously photoelectric current and intensity of light are directly proportional, so it will be a straight line. Okay, next is effect of potential on photoelectric current. So the maximum value of the photoelectric current is called saturation current. Saturation current means when current is no longer increasing. If you increase the intensity, okay, you will get a maximum value of current. Okay, so there is a diagram for experiment, you can check that in your textbook. I am not going into the detail, that will divert your mind. So photoelectric current is, light is falling, some electron is coming out and you are getting some current. Okay, so that current, the maximum value of the current is called saturation current. Okay, as you can see that as you increase the intensity of light, okay, the saturation current magnitude also increases. So there is a limit of maximum current. That limit can be increased by increasing intensity. Higher the intensity, higher is the saturation current, because it's a proportional, linear proportional relationship. Okay, saturation current correspond to the case when the photoelectrons emitted by the emitter plate reach the collector. So when emitter plate means whoever is the photosensitive material, for example zinc, cadmium or sodium, potassium, cesium, whatever you are using, okay, that is photosensitive material, and when the light is falling on it, the electrons are reaching to the collector plate. Okay, collector plate means whoever is collecting the electrons. The minimum negative potential V0 given to the plate A, which the photocurrent stops, becomes 0, is called cutoff or stopping potential. Now what is that stopping potential? You are applying a voltage in the reverse direction. Okay, so current, the electrons are coming from, say, this side to this side. Okay, electrons are coming from this side to this side, so there is a current flowing in the opposite direction. Now what you have done, you have applied a reverse voltage so that there is a current trying to cancel the photocurrent. Okay, so there is a current which is trying to cancel the photocurrent, and once that is called negative potential, obviously. So that negative potential tend to stop all the motion of electrons at a certain value. Okay, so this is called stopping potential. Stopping potential means no current is flowing in the circuit, and this stopping potential depends on the frequency of light, not on the intensity of light. As you can see, there are 3 intensity of light, and for all 3 intensities the stopping potential is same. Okay, so stopping potential is independent of intensity, it only depends on the frequency. Okay, so as you can see here, if you change the frequency, stopping potential also changes. Here we have a single intensity light. Intensity of light in this case is kept constant. 3 different lights are taken. Okay, one is nu 3, one is nu 2, one is nu 1. So there was a question in previous KCET exam. So this type of diagram was given. Okay, so as you can see that higher the frequency, higher is the cutoff potential, or higher is the stopping potential. Okay, so stopping potential or cutoff potential increases with increase in frequency. Okay, similarly as you can see that this is in between, so nu 2 is in between, so the cutoff potential also in between, and nu 1 is smaller value, this is the smallest value, so smallest value means this is the smallest cutoff frequency. Okay, so as you increase the frequency, cutoff voltage also increases. Okay, but the saturation current remains same, that only depends on intensity. Saturation current does not depend on frequency. Okay. Now, this question I was talking about, this is from one of your previous KCET year questions. So as you can see that here we have 3 lights, 1, 2 and 3, and the question was following graph represents the variation of photocurrent with anode potential for a metal surface. Here I1, I2 and I3 represents intensities, and nu 1, nu 2, nu 3 represents frequency of the 1, 2 and 3 respectively. Then you have to identify which one is the correct relation. First of all, we will check what is the intensity relation. So as you can see, these 2 lights, number 2 and number 3, they are giving you the same saturation current. So intensity of 2 and 3 must be equal. So I2 must be equal to I3. Okay, I2 must be equal to I3 because they are giving you same saturation current. Whereas 1 and 2, they have the same stopping potential. 1 and 2, they have the same stopping potential. Same stopping potential means their frequencies are equal. So nu 1 must be equals to nu 2. Okay, so nu 1 and nu 2 must be equal because they are giving you same stopping potential. Okay, and nu 3 is greater than both of them. Nu 3 is having a higher potential, cutoff potential, that means nu 3 will higher than that, but less than greater than relationship is not required to solve this question. So let's see which one is the correct. So nu 1 equals to nu 2. So we have found that nu 1 equals to nu 2. So we see that either option A or option C are correct. Either option A or option C, one of them is correct, one of them is wrong. Now if you consider option A, then you see that I1 equals to I2. Is I1 equals to I2? No, I1 is not equals to I2. So definitely A is not correct option. Next is option C. Here they have given I1 not equal to I2. So I2 equals to I3 means obviously I1 is not equals to I2. Obviously, right? I1 is not equals to I2. Okay, because I2 is equals to I3. So definitely this is the correct statement, this is the correct option for the given question. So be careful, not always you will get the correct relationship. Okay, first you have to check what are all the correct relationship, and based on that you have to identify which one is the correct answer. Okay, once you practice such questions, it should not take much than more than 30 seconds. Within 30 seconds you have to identify and solve this question. Okay, now another graph related question. related observation obviously. The stopping potential V0 varies linearly with the frequency of the incident radiation for a given photosensitive material. So here this x-axis represents stopping potential, okay, and if you see that for a given particular metal A, okay, the stopping potential and frequency are linearly proportional, but there is a minimum value of frequency, okay. This minimum value is called threshold frequency. We'll see that, okay. Other than that, this is a linear variation, but remember that it should not be from the origin, origin is only current versus intensity, frequency is not involved. As soon as frequency is involved, okay, it is not a current. So stopping potential versus frequency of the incident radiation, as you are increasing the frequency, stopping potential also increases, linear relationship. But this relationship varies from metal to metal. So this is for metal A, this is for metal B, okay. Metal B may have a higher stopping potential, but they both have a same graph. Another metal C, they will be also parallel to this, okay. Stopping potential can change based on what metal you are using, but the relationship will be same, that is straight line. There exists a certain minimum cutoff frequency nu naught, okay, for which the stopping potential is 0. So there is a certain potential nu naught for which the stopping potential is 0, okay. The maximum kinetic energy of the photoelectrons varies linearly with the frequency of incident radiation, but it is independent of its intensity. These are the implications. So as we can see, the stopping potential is independent of intensity. Very, very important point. For a frequency n of incident radiation lower than the cutoff frequency, no photoelectric emission is possible even if the intensity is large. So if the value of the intensity is value of the frequency is less than this nu naught, okay, if the frequency is less than this nu naught, there will be no photoelectric emission even if you apply very high intensity light, okay. So very, very important point to remember, okay. The minimum cutoff frequency nu naught is called threshold frequency. It is different for different metals. So threshold frequency or cutoff frequency is different for different metals, and the official name is threshold frequency, okay. Now Einstein's photoelectric emission, very important. That now what he said, that photoelectric emission does not take place by continuous absorption of energy from radiation. So initially photoelectric emission was compared to thermoionic emission, okay. In thermoionic emission, what is happening, you are heating a metal and then metal is absorbing the heat energy, and that heat energy is in turn passed to the electrons. Then the electron is getting some energy slowly, and then it is coming out of the metal surface. That is thermoionic emission. It takes some time, okay, for the entire process to happen. But the photoelectric emission is an instantaneous process. As soon as the light is falling on the metal surface, the electron is coming out, okay. So it takes about 10 to the power of -9 seconds to happen, okay. So that is why it is called instantaneous process. It does not have a visible time lag. So now to explain that, Einstein said that the process is not because of the metal surface is absorbing energy, it is happening for something else. What he said is that radiation energy is built up of discrete units, so called quanta of energy of radiation. So quanta of energy of radiation means, he said, as I say, quanta means you can consider to be a packet. So packet of milk, okay, half liter is the minimum purchasing packet that you can purchase from shops, right? Similarly, it is like a quanta of milk, that is called a quanta of milk. Here it is quanta of energy, okay. So everything is consisting of a single packet, and minimum energy that is possessed by the photons is basically, that is called the quanta. So the concept of photon came here for the first time, okay. Each quantum of radiant energy has an energy h nu, okay. Nu is the frequency, h is Planck's constant, okay, where h is Planck's constant and nu is the frequency of light. Okay, the maximum kinetic energy of the emitted electron is given by Einstein photoelectric emission. So what he said is that whatever quantum energy is getting transferred to the electron, it is getting transferred to the electron directly. The metal is not involved here. That is why it is an instantaneous process. Okay, so in the heating process, heat is being slowly transferred from the metal to the electrons, then electrons are coming out. So this is a slow process. But in case of photoelectric emission, the light is falling on the metal, the electrons directly absorbing the photons and coming out of the metal surface. Okay, now when the electrons are coming out of the metal surface, definitely it will possess some kinetic energy. So what is the equation for that kinetic energy? He said that the maximum kinetic energy is basically h nu minus phi naught. So h nu, we know that is the energy of the incident photon, phi naught is the work function of the metal surface. Okay, we will see one problem. Light of two different frequencies whose photons have energies 1 electron volt and 2.5 electron volts respectively, successively illuminated by a metallic surface whose work function is 0.5 eV. Ratio of maximum speeds of the emitted electrons will be. So energies are 1 electron volt and 2.5 electron volt. Okay, so what is the K max 1 is 1 electron volt minus 0.5. 0.5 is the work function. Work function is the minimum energy required to free one electron. Okay, so minimum energy required is 0.5 eV. So K1 max is 0.5 eV and Km2, the maximum kinetic energy due to the second second wave is 2.5 minus 0.5, that is 2 eV. Okay, you have to remember the order, the same order you have to solve it. Now what is the ratio? Km1 by Km2 equals to 0.5 by 2, that is 1 by 4. Now what is Km? Km is half mv square, so half mv1 square by half mv2 square. Here m is the mass of electrons, so they are same. So mass of electrons are same, so 1 by 4, or v1 by v2 equals to square root of 1 by 4, that is 1 by 2. So ratio is v1 is to v2, v1 is to v2 is 1 is to 2. So the ratio is 1 is to 2, not 1 is to 4. Okay, so be careful. Simple problem, you can solve it again. This is a 30-second problem. If you practice enough, you can solve such questions in less than 30 seconds as well. Okay, so easy question, typical question that coming from your KCET exam. So you have to practice such questions again and again. Now Einstein, continuing with the equation. Okay, this one I think I have, oh sorry, I'm going back, sorry. So now let's move on. So let us discuss about the work function a little bit more. In the equation, the work function is given by phi naught equals to h nu naught. What is nu naught? We have learned the cutoff frequency or threshold frequency. So the work function is nothing but h nu naught. Okay, this is the minimum energy required to free one electron. Okay, here nu naught is the threshold frequency, so the name we already know about it, but how to utilize that? So Einstein gave us the idea to how to utilize the threshold frequency. So everything was known experimentally, the theoretical explanation was not there, so for which Einstein came and helped it. Okay, the Einstein photoelectric equation in terms of the stopping potential is given by EV naught equals to h nu plus nu naught. So there are same equation can be written in 3-4 different forms. So first of all, K max equals to h nu minus phi naught. Okay, h nu is the energy of the incident photon. Sometimes you can write this as energy of the incident photon minus phi naught. Okay, sometimes you write this as half mv square equals to h nu minus h nu naught. Okay, or half mv square equals to h nu minus nu naught. This is another form. These are all the forms of the same equation, and sometimes it is written as EV naught, this is stopping potential, equals to H nu minus nu naught. Okay, or sometimes you can also apply H C by lambda minus C by lambda naught. Okay, lambda in terms of wavelength. Okay, same equation, all the different forms based on whatever is given to your question. Okay, so you have to remember all these forms based on what type of questions is coming. If you have solved your this year PU question paper, there was one question based on the lambda function. Okay, so also you can take C common over here. HC equals to 1 by lambda minus 1 by lambda naught. Okay, and value of HC is approximately 1240 EV per nanometer. Okay, EV nanometer. Why nanometer? Because lambda is sometimes given in terms of nanometer, so you have to careful. If you are using the nanometer form of lambda, then this is the form you have to use. Okay, now so these are all the different forms. As I said, EV naught equals to H nu plus H nu naught. Okay, now photon. And in interaction of radiation with matter, radiation behaves as if it is made up of particles called photons. So as I said, electrons are absorbing the energy. So what is happening is, there you can imagine this as a collision between two particles. So there was one ball and you are hitting with another ball, and the ball starts moving immediately after collision. So basically you can consider the motion of electron as a collision between the light and the electron. Now how can light be colliding with a particle? Electron is a particle, light is a wave. How can they collide with each other? So that collision is only possible if light is not a wave, it is basically a photon. So while interacting with electron or smaller particles, light behaves as a particle itself. Okay, that is called photons. Those particles are called photons. Okay, each photon has an energy E equals to H nu and momentum P equals to H nu by C. So as we know that for a moving particle, they should have some energy as well as momentum. Okay, now you have to remember that the rest mass of photon, that is when you stop, if you want to stop a photon and measure its mass is 0, rest mass is 0, but still it has a momentum. Okay, for that definitely you have to study little bit higher order, special theory of relativity. How can a moving particle have mass? What at static condition it may not have that mass. So those are difficult concepts. I am not going to discuss that, but you have to remember that as long as a particle has a momentum and energy, it is considered to be a particle. Okay, obviously it is moving with the speed of light, so C is given in the equation. All photons of light of a particular frequency nu or wavelength lambda have the same energy. So for that means that if a red light is coming, okay, red light, all the photons, red light is consisting of multiple photons, all the photons have same amount of energy. Okay, it is not like that if you do some experiment with red light in India, you will measure a different energy. If you are doing it outer space, you will get a different energy. No, everywhere, wherever you do experiment with red light, all the photons coming out of the red light, you will have the same energy. Okay, energy is constant as long as obviously frequency is same. Okay, so energy is H nu or Hc by lambda, and momentum is also constant, H nu by C or H by lambda. So momentum for a wave can be calculated by this H by lambda formula, whatever is the intensity of radiation may be. So momentum and energy does not depend on the intensity. Intensity means more amount of photon is coming out. Okay, but total amount of photons is increasing, but individually a single photon will still have the same amount of energy. So that is why it is independent of the intensity of light. Photon energy is independent of the intensity of radiation. Obviously I explained that. Now let's move on. photons are electrically neutral and are not deflected by electric and magnetic fields. So they do not have any electric properties, they do not experience any force by electric or magnetic fields. In a photon particle collision, such as photon electron collision, the total energy and the total momentum are conserved. Very, very important. Okay, so when photon particle or photon whenever they are colliding, total energy will be conserved and total momentum will also be conserved. Okay, however, the number of photons may not be conserved in a collision. So what is the meaning of that? Suppose an electron is colliding with a photon. Okay, electron absorbed the photon completely. So photon is gone now, right? Photon is 0, number of photon is now 0 if the electron absorbs the photon completely, right? So number of photons may not be the same, but the total energy and total momentum will be conserved, still be conserved. Okay, the photon may be absorbed or a new photon may be created. Sometimes what happens is that electron absorbs the complete photon and then releases a different frequency photons. Okay, that is also possible sometimes. Okay, so now wave nature of matter, this is very, very interesting. Now so far what we have studied? We have studied particle nature of waves. Okay, that is light, which is a wave, it is behaving like a particle. Okay, particle means just like your ball, cricket ball or badminton cork, whatever you are using, that is like a particle, right? So light was behaving like that. Now there is a person called Louis de Broglie. He came up with this beautiful idea that nature was symmetrical and that two basic physical entities, matter and energy, must have symmetrical character. So we know that matter can be converted into energy, energy can be converted into matter, right? So last class I think I discussed it about it, Einstein's equation, E is equal to mc square, and also from energy you can create matter. For example, if from an energy you can create electron positron pair. Okay, electron and positron are matter, and they matter and antimatter, and they can be created from energy. So energy can create matter, also matter can create energy. Okay, if you destroy the matter you will get back the energy. So that is why it is very important to know that they are like brothers. So you can consider that they are symmetrical. Now if radiation shows dual aspects, so should matter. Now this person said that radiation wave is basically a radiation, right? Electromagnetic waves are considered to be radiation. Okay, so if the electromagnetic wave can show its matter properties, then matter can also show its wave properties. So and that person is Louis de Broglie. Louis de Broglie was a very interesting story. He was a history student in some college, okay, and his seniors was discussing about the discovery of Einstein's photoelectric emission, and from there he learned about, okay, light behaves like a matter particle. Okay, from there from that coffee table discussion he took this matter, he learned some mathematics, and then he derived that, okay, if a particle is behaving like a wave, its momentum should be h by lambda. Okay, and you can even calculate the wavelength of the matter wave, and he said this is called matter wave, and lambda is basically h by p. So if it is moving with some momentum, okay, you can calculate its wavelength. Okay, now if you have to remember that h value of h is very, very small, 10 to the power of minus 34. So to observe a sizable wavelength, the p has to be very, very high. So if it is moving with a very high speed, okay, almost equal to the speed of light, then only you can comparably see the wave. Okay, and that wave nature is not possible with you, me, or all the big particles we know. Okay, I cannot become a wave even though it is shown in some of the science fiction movies, but that is not possible. Our wavelength will be so small, we will not be able to do anything. Okay, so that is very, very important. So wavelength, to observe a wavelength, it has to have some very high speed. Okay, this is called de Broglie wavelength. Now see one question. Find the de Broglie wavelength for an electron with kinetic energy 125 electron volts. So energy is given 125 eV. Sir, energy is given. How can I calculate the wavelength? Sir, you told me the formula of wavelength is h by p. So how can I calculate p? So to do that, what you have to do, first of all, you have to convert, first thing first, you have to convert this EV into joules. So 125 into 1.6 into 10 to the power of minus 19 joules. This is the energy of the electron. Okay, now there is a relationship that you have to remember, P equals to square root of 2me. Now how this came into existence, I will teach that in your first PU class, first PU division class. Okay, if you remember it, very good. If you don't remember it, you can check that when we are doing the motion in a work energy power, right? Work energy power chapter, when we are revising that chapter. So P is equal to 2me square root 2me. Now you have to put the values. Okay, 2 into mass of electron is 9 into 10 to the power of minus 31. Okay, and energy you can have 125 into 1.6 into 10 to the power of minus 19. Okay, so you will get 9 square root is 3. Now 2 into 125 is 250. 250 into 1.6. 250 into 1.6 means you can cancel this 0 and this 1.6 will become 16. Okay, so this will become 16. Now it is easy. Now let's see the 10 to the power of minus 31 minus 19. Minus 31 minus 19, 0, 60. So square root means 10 to the power of minus 30. Right, it will be half of that value. Oh, sorry, I made a mistake. It will be 50. It is 50. Okay, 50 means it will be 10 to the power of minus 25. Don't worry too much. Maybe mathematically you think that this is very difficult. Actually, it is not. So square root of 25 is 5. Square root of 16 is 4. So into 10 to the power of minus 25. So it will be 15 into 4 is 60. 60 into 10 to the power of minus 25, or 6 into 10 to the power of minus 24. Okay, now let's convert it into wavelength. So wavelength is h by p. So problem is not yet solved. 6.6 into 10 to the power of minus 34 divided by 6 into 10 to the power of minus 24. Okay, so you will get 1.1 and you will get 10 to the power of, so it will be 1.1 into 10 to the power of minus 34. This will go up and it will become plus 24. So that will be minus 10. Okay, now if you check, all the answers are given in nanometers, so you have to convert it into nanometers. So what you have to do, you have to 0.11 into 10 to the power of minus 9 meters, 0.11 nanometers. So 0.11 nanometers. So correct answer is option D. Okay, if it is given in picometer option, if it is given in the picometer option, the question actually was in picometer. I have converted into nanometer so that you can understand it. Now if the same question was given in picometer option, then what you have to do, you have to multiply with 100. Picometer means 10 to the power of minus 12. So and you have to increase the power to 10 to the power of minus 12. Okay. So be careful what unit is given. If you are using all the SI values, the final answer should only be in SI unit. Okay, final answer will only be in SI unit. Okay, now based on whatever option is given, you have to convert the unit accordingly. So in that case, it will be 110 picometer. Okay, so 110 picometer, if it is given in nanometer option, then you have to divide it by 10. If you have to go to smaller units, picometer, you have to multiply with 100. Okay, based on whatever answer you are getting, you have to adjust your answer accordingly, right? Now if you have liked this lecture, don't forget to give it a thumbs up, subscribe to our channel if you have not subscribed, and obviously register for Abhyas KCET test series. Okay, I'll be back with a new lecture very soon. Till then, bye.